There we go. First thing, write the derivative in Leibniz notation and state the units. So side note before I write the actual answer for this case, but remember it looks like some dy over dx, which in this case for us would be our correct variables would be dp over dt. Something I don't think I said the other day, these d's are always lowercase. Do not make them uppercase. That's not correct notation. That doesn't really mean anything. So it kind of matters that they're lowercase. So keep them lowercase always and forever. Erase. Of course, these things are whatever they are. If they're capital, leave them capital. If they're lowercase, leave them lowercase. But why is my erase button being weird? So remember, the nice thing about Leibniz is that the units just kind of fall out for us. So the units of P was in people, so this would be in people per year. If you put year since 2010, sure, but it's technically just years. So, and then we want to interpret f of 10 and f prime of 10. So f of 10 is just kind of a usual value, if you will. So that's just saying 10 years after 10 years after 2000. 220 people. So I could say something like in 2010, the population is 220 people. And then for our derivative, we kind of have those two options. I find most people usually do the right way, so I'm just going to write that one down. I'm going to say after 2010. Sure, with the other thing there, we already were kind of specified, but I'll just be extra nice, extra good about it and put it in there as well. So after 2010, the population is increasing by 15 people per year. The other way would have been after 2010, something like each additional year. Maybe I should say for each additional year, the population increases. That says increases. I kind of put the S behind the Y, but anyway, by 15 people. So you kind of have your two options there. One or the other, whichever one floats your boat. And then our last piece is when we want to estimate different values of the function. So essentially, this is where we have to use what we're given, and the only things we're given are f of 10 and f prime of 10, so we have to use that value. So if I want to estimate f of 20, well, I have to start at f of 10 because that's the only value I know. And then I can use the derivative value to essentially tell me how much I increase or decrease by, depending on whether I'm going up or down. The difference between what I want and what I have is 10, so I need to take 10 steps essentially to the right, if you will. So I want to multiply that value by 10. So we'll have 220 plus 10 times 15. I'm going off of memory from my class yesterday. This should be 370. Exactly. And then no, I shut her up. I don't even know which computer that's coming from or how I make that happen. But anyway, f of 5, it's probably because I accidentally pressed that. That's probably it. Anyway, f of 5, I still need to start. Let me move up a little bit. I still need to start at 10 because that's the only value I actually know for sure. And I still want to use f prime of 10. But now, from where I'm starting to where I want to be, I have to go backwards 5. So I'm going to have to either add on a negative times the thing or just subtract it. Same idea. So we'll have 220 minus 5 times 15. 5 times 15 is 75. So this turns into 145. You shake your head, so I'm looking at you for confirmation. Okay, cool. Questions, concerns on that one at all? Any of that? Yeah.
Okay, so for 5,
They're now all labeled Part A because I broke it up.
the first one. Okay, I usually have like the dt over dt. Wait, so really that's not how you do it.
So it always has to be the y value on top. So since we're given, let me not go away from where I'm talking here. Since we're given p equals f of t, oh my goodness, my pen, which kind of looks like x, my Leibniz notation has to be the y value on top and the x value on the bottom.
Oh.
So since in our case the p values are kind of like our y's, it needs to be dp over dt. Yeah. For which one? The last one?
Yeah.
What did you do?
I did it a whole lot of function. But then I ended up just dividing it by 5 and then like basically like where it says minus 5 times delta, I just divide it. It works for everything.
Do you have it written somewhere? No. Yeah, can you write out? So, if it's correct mathematics, sure. But what you're saying scares me.
I know, I bought online because I didn't fully start watching.
Okay, maybe then? I mean, maybe? Sure. Yeah, like, I don't mind how you do things as long as it's correct math. It's just that sometimes I've had people get the right answer, but it's not math. So as long as it makes mathematical sense, whatever floats your boat. But I'd have to see it to know. But anyway, any more questions about any of that? If you're getting them right, I would hopefully assume that it's some kind of correct process. Anyway. So here we're given the original graph and we want to find which one's the derivative graph. So remember for that, the first thing we kind of want to look at is our maxes and our mins. That blue is very light. I thought it was a darker blue. Well, it shows up. Anyway. So we have, kind of our maxes and mins. We don't care whether it's one or the other at -2, +1, and 3. So that means that our derivative should cross the x-axis at those 3 points and only those 3 points. So that essentially knocks out this last option because it does cross at -2, but it doesn't cross at +1 or +3. It crosses at these kind of 2 other spots that aren't the correct spots. So that's not it. So then we're kind of between these top 2, and this is where we kind of have to go back and look at the increasing and decreasing piece. So we have a decreasing piece, then an increasing piece, then a decreasing, then an increasing, which would mean that our derivative should be negative, and then positive, and then negative, and then positive. So we need something that starts below the x-axis, then changes to above, and so on. So the only one that does that is this first option on the left, because the option on the right is essentially it crosses in the right spots, but it's just kind of the wrong positive negative order, if you will. Questions, concerns on that? All righty. Okay, so then let's go back to our notes. We started kind of 2.4 the other day, so we got to finish 2.4 and also hopefully finish 2.5. They're both really short. Where's 2.4? There it is. So this is what we got through the other day. Should be up there. No. So the first thing we're going to do is actually kind of review what we just wrote down, because we're going to write it down in a bit more of a concise way. So that's kind of nice that we'll just exactly review what we already looked at. So essentially what we're building here is we kind of have now these relationships between the original function f prime and f double prime now. So this table is kind of going to write exactly what is written above in the notes, just in a more concise way. I would suggest committing this table to memory because it's used that often. And you will want to know the relationships between these three types of functions: backwards, forwards, sideways, and any other way you can think of. So we had this first relationship, which we actually looked back in 2.2, which was that if the original function is increasing, if my pen will write correctly, then the derivative is positive. And if the original function is decreasing, then the first derivative is negative. Just from that relationship, we can't say anything about f double prime yet. So that was kind of back from 2.2, but then what we developed now in 2.4 is that this kind of relationship also holds between the first derivative and the second derivative. So if the first derivative is increasing, then the second derivative is positive. And if the first derivative is decreasing, then the second derivative is negative. It's kind of like we take this relationship and just kind of shift it over a little bit. If you wanted to, you could continue shifting it over and just keep on adding derivatives, but because technically you can have the third and fourth and fifth and sixth and seventh and eighth and ninth derivative and so on and so forth. We only care about the first and the second ones, but because after that they stop meaning anything in terms of context. It's just for giggles. But anyway. But then we also have the relationship that if the second derivative is positive, then if the second derivative is positive, then the original function is concave up. And if the second derivative is negative, then the original is concave down. Nope. So don't worry, I'm leaving it up there. I'm just trying to scroll up a little. No, too far. Come back. Tiny bit. There we go. Good enough. So you want to know the relationship between all of these. Also, like if concave down means that the first derivative is decreasing, you can also have to go between those two as well. But anyway, so you'll want to know that table and those relationships pretty well. To visualize concavity, we kind of wrote this down before, way back in chapter 1, but I'm going to do it again because now we have these kind of new pieces in terms of the derivative values. So just to remind us, so this whole piece is concave up, and this whole piece is concave down. We know that if it's concave up, then that means that the first derivative is increasing versus the first derivative being decreasing for concave down, and that's for both of those kind of pieces of those. But then we kind of have two options for each one. One of them where the function is decreasing and one of them where the function is increasing, which would mean that the derivative, first derivative, is negative and positive respectively. And then for the concave down option, same idea. You have one that's increasing, one that's decreasing. So the first derivative would be positive and negative respectively. Give you all a couple seconds to take that down. We'll do a couple examples and then we're done 2.4. Right. Scrolling. I don't know why this just scrolls like an idiot. So for the given graphs, determine where their second derivatives are positive and when they are negative. So we've got these. I'm going to split this up so that I don't write too much each piece. So again, we've kind of got our concave up and concave down options. So if we look at option A, part A, that entire graph just looks like the entire concave up like option. Looks like the whole entire thing. So we would say that the second derivative of this function, since it's always concave up, so let me write that. So concave up everywhere. So if it's concave up, then the second derivative is positive. So since this is named f, which I only point out because the other ones are not, we would say that, whoops, I've already missed it. The second derivative is positive everywhere. You could say on negative infinity to infinity if that makes you happier. You know, whatever says that it's through that entire graph. For part B, well, that's not exactly like a full option of one of the two, but it does look like a half because we kind of have like 4 options here. One thing I'll say to help you, this one might, no, I'm not going to say that. Anyway, if you're having trouble seeing these, another thing that you can look at is this graph is increasing. And for each concave up and concave up, it's only got one option that's increasing. So like for the concave up piece, this is the increasing option. And for the concave down piece, this is the increasing option. So we're kind of just looking between option 2 and 3, if you'll let me call them that. So which one of those two does it most look like? Option 3. So this would be concave down everywhere. It also essentially is the whole entire graph. It doesn't change to be looking like anything else anywhere else. So we would say, now this one's named G. So we would say the second derivative of G is less than 0. Concave down, second derivative is negative. Everywhere, or on negative infinity to infinity if you like. Now this last one actually changes a little bit. It's going to change exactly here at the origin at x equals 0. So if we look at this first piece, well, that's increasing. So we're kind of looking at the two same options again, option 2 versus option 3, because those are the only increasing pieces. Which one does it most resemble? Option 3. So that piece would be concave down. I'll write the second derivative piece in a minute. And then the second half, well, that's also increasing. So I shouldn't have erased it. We're looking at the same two options again. Option 2 versus option 3. Which one does it most resemble? Hopefully option 2. I'm kind of going through this kind of fast because to me, well, nope, don't say that. Hopefully, nope, I'm going to shut up. Concave. Up. Everything I'm thinking of saying sounds condescending, and I don't want to sound condescending. So since this function is named h, we're going to say that h double prime of x is less than 0. So less than 0 means that it's concave down, so that it was concave down from negative infinity to 0. I'm going to go ahead and put a bracket on that. I'll talk about that in a second. And then it's positive, so if the second derivative is positive, then it's concave up, so it was concave up on 0 to infinity. Brackets versus parentheses, just like with increasing or decreasing intervals, it kind of doesn't matter as long as you never put a bracket on an infinity. Because just like with increasing or decreasing, it doesn't make sense to say a single point is concave up or concave down. So since you have to include an interval, you can include it in there or not, whatever floats your boat. So if you always want to include it, you always want to exclude it, whatever floats your boat. I don't know why I erased those, but anyway. Questions, concerns on that? This is the main thing from 2-4 is you just want to be able to look at a graph and recognize the pieces for what they are and what they mean about the derivative values. Yeah. So that is going to be a point of inflection. Words that I want. So officially, concavity is 0 at an inflection point. Some people don't know what I'm talking about, but he knows what I'm talking about. An inflection point concavity is going to be, I shouldn't say concavity is 0. The second derivative is equal to 0, which would kind of make you want to say that there's no concavity there. But people come together and agree with the fact that just including it in this interval doesn't really change anything. It's not trying to take away from the fact that that's an inflection point, but just including that singular point in that interval doesn't really make a difference. So, well, yes, I agree, it's an inflection point, and therefore there's no concavity at that singular point. When we're listing these intervals of concavity, since that singular point doesn't really change the fact that it stops there, people kind of agree that it can be added in if you want to. It's a little bit of a nuance where people are like, when we're listing intervals, who cares? Kind of idea. Yes, Kira. So yeah, it's a bit wishy-washy. And if you just want to say, well, it's an inflection point, so I'm not going to include it, feel free to. Some people definitely are like, no, it's an inflection point, I'm not including it in any interval. And other people are like, it doesn't matter. So it's kind of a personal preference kind of thing. Yeah, Kira. B. So let me scroll up the tiniest bit. This function is increasing. So since this function is increasing, I kind of have two options. Let me scroll up a whole bunch more. Can I fit it all in one thing? No, I can't. But my function is increasing. Now I only have two options for concavity when f is increasing. I have this option on this side, kind of like the right side of the concave up piece, and I have the left side of the concave down piece. So let me scroll back down really quick, because I can also, I don't know why I scrolled up for this, but anyway, scroll back down. So we kind of just have these two options for this function. My circles are going to be too confusing. Can I do a different color? Yes, I can. Red. So those two options are increasing. Now, looking at that graph of B, which one does it look more like? Option 2 or option 3? And does it ever change and look like kind of like one of them in one spot and another one in another spot? It actually it most resembles this kind of third option, and it doesn't really change to look like this other guy anywhere else. So since it kind of looks like that third option through the whole entire graph, it would be concave down everywhere. Does that make sense? I know that was like kind of wishy-washy, but it's kind of just, you just got to look at it and kind of see which one it resembles the most closely. That wasn't English. So at this point in time, we're doing this all by sight. We just have to look and try to trust that our eyes know which one it is. We will be getting to a point where we can actually kind of find these pieces algebraically. We can find the pieces that are concave up versus concave down with actual math instead of just our eyes. But we're just not there yet. Okay. Any more questions before I move on? Okay, cool. So if you think about the derivative is a rate of change. It's a slope. So what the second derivative is actually a slope of a slope. It's a rate of change of a rate of change. So we can also think about it as essentially, how is the slope changing? So say I have this table here, years related to the number of car sales, and on to eventually work up to talking about the second derivative. But the first thing they're going to ask me to do is to find the average rate of change, so that's review, if you will, for each consecutive interval. So I'm going to kind of create a new table for these average rate of change values. I'm also going to name it change in C over change in T, just for, well, not really, but I kind of have a point to it. So we're going to go from 1972 to 1975, and then from 1975 to 1980, 1980 to 1985. I should make this table smaller. Well, then it cuts off half the, anyway. 1985 to 1990, or I should just, I'm just talking to myself, don't mind me. 1990 to 1995, 1995 to 2000, and 2000 to 2005. Woo! Now I want to find all of those average rates of change. I'm going to find 2 of them fully and then just tell you what the rest of them are. Because I trust and believe, hopefully, that y'all can find it once I remind you what it is in case you've forgotten. So if we're going between these first 2, remember the average rate of change is essentially the slope between those 2 points. So we're just doing this 1034 minus 587, 1975 minus 1972, which would turn out to be 149. And again, I'm just going to write officially that second one, and then I'm just going to tell you what the values are. So this next set would be our fifth. Where'd you go? Come back. 1554 minus 1034, 1980 minus 1975, which gives us 104. Same idea for the rest of them. You get 7, 4, negative 50, negative 9.2, negative 21.4. So, what can be said about the sign of the second derivative, which is written in Leibniz notation, but notation for the second derivative? So all we have here is an average rate of change. Now this would essentially be a first derivative because these are slopes. So that might not be exact, but it's at least an estimate for our derivative value. So if we wanted to talk about the second derivative, we would want to look at how these slope values are changing. So if we kind of look at this table here, these values from 149 all the way down to negative 50, through that entire kind of interval, if you will, those values are decreasing, right? Now, there is going to be some strange overlap in this question, and it's just because of the weird way we had to do these ranges, okay? So there's a little bit of ambiguity here, but hopefully y'all still trust and believe what I tell you. Oh my God, change. Now this is where I'm going to have some weird overlap. If I start at negative 50 and go up to negative 9.2, between those 2 values I increase, right? Yes, I have this weird overlap, but let's forget about that for a second. And now some more overlap. And I know now you could say, well, what about the whole entire thing then? Can't the whole entire thing be decreasing? Well, no, because those 2 values in the middle kind of increase. But then between negative 9.2 and negative 21.4, I decreased again, right? Now again, the only reason we have this overlap is because we're talking about these in terms of ranges. We don't have a set value to stop at. We're stopping in the middle of a range, and maybe we don't know where, so we're just going to take the entire set of the range. Does that make any sense? So that's the only reason why there's like this wishy-washy overlap. But we can still talk about this in the way we're going to. So essentially what would happen here is, so the slopes are decreasing. What the heck happened with my pen there? Decreasing between 1972 to 1995. Again, it probably stops somewhere in the middle of that 1999 to 1995 range, but we don't know where, so let's just say the entire range. So the second derivative, since my slopes are decreasing, would my second derivative be positive or negative? What do you think? Negative. If your slopes are decreasing, the second derivative is negative. So we would say that kind of in that interval, with a little bit of the wishy-washiness at the end, would be the second derivative would be negative. Now I could also then come and say slopes are increasing. And I know this sounds weird because I'm saying 1990 to 2000, but I've already covered 1990 to 1995. It's just the overlap because we had to work over ranges. 2000. So the second derivative is positive there. And then back to negative for that other last kind of interval, which again is kind of wishy-washy, overlappy, but just because of the way that it had to be phrased. Yeah. So she was curious as to essentially why those squareds turn out to be where they are in the Leibniz notation. So first derivative in Leibniz notation is dy over dx. If I wanted to write in symbols, take the derivative in Leibniz notation, if I wanted to tell someone to take the derivative of that derivative, I would tell them to do this. Which essentially, if you just, so there's two d's, but only one y, and then there's, essentially, it's kind of actually dx all squared, but no one ever writes the parentheses because mathematicians are lazy, or I don't know. But anyway, that's kind of why the squared turns out where it is. So yeah. Yeah. So I should finish this out really quick. So slopes are decreasing again. Again, super wishy-washy with those overlaps. But I hope you still agree that if I say from negative 9.2 to negative 21.4, those values are decreasing. I think we kind of agree with that, even though there's kind of that wishy-washy of that. I already included the negative 9.2. So 19... So let me even put a side note over here for anyone who's kind of looking back at this later, or maybe someone who wasn't here and looks at this later. Overlaps happen since year. So think about, like, if the 1990 to 1995 was just a number, it would kind of be included in both options, but it would be the starting point of the one and the ending point of the other. That's kind of the idea. It's just since there's a range, it just looks super weird because there's that overlap. But anyway, questions, concerns on that idea? Cool. Ooh, really? Okay. So then we're going to go to 2.5. There's one tiny last thing I wanted to talk about in 2.4, but I'm just going to hit it on Tuesday. Because there's like one question in your homework that you might struggle with. You can do it. You just might not realize the things that you need to connect might not connect in your brain until I talk about it. But anyway, let's start 2.5, and I'll get that on Tuesday. 2.5, 2.5, here we go. So marginal cost and revenue. Now, technically there's also marginal profit, but this kind of doesn't focus on profit very much. But so far we've only discussed linear cost and revenue functions, but they can be absolutely any type of function they want to be. So we still want to be able to talk about marginal cost and marginal revenue. So, specifically considering the cost function, the y, am I going to draw? No, I'm not. I need to set that up. The y-intercept will be the fixed cost. Now, I specifically say considering costs because fixed revenue and fixed profit I don't want to say they don't exist. It's just that we don't really ever refer to them as such. Are not referred to as such. So technically, profit and revenue functions still do have a y-intercept. So it's not that they don't have a y-intercept, so you could say fixed revenue and fixed profit, but most people are going to look at you weird because you usually just don't use that phrasing. It's usually referred to just as a fixed cost. But it does, like the y-intercept of revenue and profit is still going to tell you the revenue or profit when you don't sell anything, which is exactly what the fixed cost is doing. But then regardless of the equation, the slope will be the marginal cost or marginal revenue or marginal profit. So the marginal is used across any of them. You can refer to that and no one's going to look at you weird. Which, well, how do we find the slope if it's not a linear function? We're going to find that using the derivative. Because the derivative is a slope. Derivative is a slope. You don't have that connection in your brain yet. Connect them. The derivative is a slope. So, move. Now, we just kind of talked about the marginal, and then we're going to do something that doesn't have to do with marginal. But anyway, here we've got a cost and revenue function, and they're plotted here. So the revenue one is the linear one, is the straight line. I think those labels are very poorly placed to figure out which one's which. So the straight line is the revenue, and the curvy guy is cost. So for what production values does the firm actually make profit? Well, can anyone tell me what they think would need to happen for them to make profit? How we would want to compare revenue to cost? Exactly. Revenue would be higher than cost. Because of math, I actually have no idea who said that, but good job. So if you think about it, if we want profit to be positive, but profit is revenue minus cost, if I add cost over to the other side, then revenue must be greater than cost. So that's kind of the algebraic way to get yourself there if it doesn't just kind of click in your brain, which is fine. So where on this graph does the revenue, that linear straight line, end up above the curvy one? Just in kind of this area, kind of in the middle. So we would say that they make profit I'm going to write it like this. Q is less than 250 but greater than 130. Notice I don't include 130 and 215 because those would be break-even points and I would make no profit, and that's not fun. I actually want to make some money. I don't want to, have to go home to my mom and be like, it made nothing. I don't have anything for you, mother. And then she'll be sad. No, oh. All right, tough crowd. All right, okay. Moving on. So say you work for a company that sells mattresses, and you're asked to decide. Your boss comes up to you and they're like, "Hey, should we sell the next mattress? We've been selling 100 mattresses every week. Should we really push for that 101st mattress?" And you're like, "Ugh, I don't know." What would you maybe want to consider for them to tell them whether or not they should make that next, whether they should take the time and the effort to make another mattress to sell? Does anyone have an idea about what maybe you would want to happen? Yeah. Yeah. So that's kind of taking it deeper, but so we can do it. I'm not saying you're wrong, you're right. But the main thing we also want to focus on is kind of the marginal profit. Do they make more money when they make that extra mattress? Does it gain them more revenue than it took them to make it? Because you could say that, say the profit of making 100 mattresses. So the profit of making 100 mattresses, I'm going to use small numbers just for our sanity, is $10. So the profit of selling 100 mattresses is $10. And then the profit of selling 101 mattresses is $8. Well, then you don't want to sell that 101st mattress because you've somehow lost $2. It must have been somewhere in that cost of making it. It kind of got eaten by that revenue. It couldn't make up for it. So even though you're still making profit in general, you're making less profit than you were before, which that's not cool. So what we would want to do here is if we want to talk about whether or not it's wise to make the next item, you'd want to make, my pen is freaking out, more profit. So we'd essentially want marginal profit to be positive. You'd want to make more money than you were before. Now some notation. Marginal cost sometimes will literally just be referred to as MC. But it is the derivative of the cost function. Marginal revenue is the derivative of revenue. Marginal profit, now since profit is, pi, but they'll just refer it to MP, although I don't think they usually do that. I think they usually just use MC and MR in that case, and they never refer to marginal profit. I should say, though, marginal profit is also equal to the marginal revenue minus the marginal cost. So just like regular profit is revenue minus cost, marginal profit is marginal revenue minus marginal cost. That's probably a really important relationship you might want to remember. Profit. So kind of coming back up here, now that I have the notation to actually use, what we would want is we would want that marginal profit to be positive. So then marginal revenue minus marginal cost would have to be positive. So kind of the same kind of thing that happens in the thing we just did, where marginal revenue will have to end up being greater than marginal cost. That is I don't like that. There, that looks nice. Now, approximately, marginal cost or revenue or profit. No, where am I? Would be equal to essentially the cost of making Q plus 1 minus the cost of Q. I'm going to say this is just a note, because I think people focus on that way more than they should. The thing you really want to focus on when you see marginal cost is the derivative. But it can be approximated in that way. But the thing you want to have in your brain more is the derivative of cost. Okay, I want to get at least this one example, if not both of them. There's only 2 more examples, then we're done 2.5. Told you they were short. I've got a couple of minutes. I might just be able to get through the first one, but the second one is similar, so. Oh, I forgot to draw the little line on here. Whoopsies! This doesn't make sense if I don't tell you where the 100th one is. So that's going to be about right there. So say you're working with that mattress store, and the guy wants to know whether or not to make the 101st mattress. And all he does is he gives you this cost and revenue graph, and he's like, here, figure it out. And you're like, great, thanks, boss. And this is all you got to figure out whether they should make the next one or not. You don't know what the equations are. You barely even know the values. He just gives you this graph and walks away. And you're like, you're the best. So this is where we can still figure it out, though. Now, one thing I want to stress, now I should have had this on here already. I forgot to draw that already. If you want to talk about whether or not you should make the 101st, you want to look at the slope at 100, okay? So whatever one you're talking about making, you want to look at the slope of the one before it. Because if you think about what slope means, slope is telling you if you increase by 1. So if we want to increase to the 101st, we want to talk about the slope at 100, which is a big thing that lots of people always forget. So I want to look essentially at the slopes of these two lines because I want to talk about the marginal revenue versus the marginal cost. What I want to find is I want to know whether or not marginal revenue is greater than marginal cost. Well, remember, the derivative is a slope. So if I look at the slopes of these functions, I can just figure that out. So let me look at the slope of the cost function. Well, that's kind of looking something like this. And then if I look at the slope, what are the words, of the cost function, I think I said those backwards. That's looking pretty straight line already. So between those two kind of, let me give this one some arrows because I think it's kind of slipping into the red one kind of stands out, but the black one might have been slipping a little bit. Which one of those two lines has a bigger slope? The black one, right? Because the black one is steeper than the red one. So the black one was on our revenue function. So since the slope of R of Q is steeper at Q equals 100 than the slope of C of Q, we can say that the marginal revenue is greater than the marginal cost. So they should make a 101st mattress. Because since their marginal revenue is greater than their marginal cost, that's going to mean that their marginal profit is going to be positive. They're going to make more money. So even if you don't have functions, you don't have values, if you can just find the slopes and kind of compare the steepness of those two lines, you can still talk about marginal profit, marginal revenue, marginal cost, all that jazz. So there's one more example in 2.5. It's a very similar idea using the slopes, but we'll talk about that. We'll get that one on Tuesday. I'll do that last bit of the thing from 2.4 on Tuesday. So there might be like one or two questions that you have a little bit of iffiness on the homework, but the large majority of it, you now have the material you need to do it. My voice just keeps breaking. I don't think I have anything else to say besides let's take a quiz. Okay. I need to stop the recording. I need to take this off the big screen so that people don't see lots of other people.